Yeah. Oh, sorry. Yeah, seems to be a lot of stuff here. So all of you can see the whiteboard?
Yes, sir, we can.
Yeah. So very quickly in the first 10 minutes, let us wrap up the questions, and I'm not going to solve them. I'm just sort of going to point out how they were solved or how they should be solved. So you all remember the two questions, and I hope you all remember. I think the first question was a very easy, simple thing about a column with enzymes packed, and obviously I did not introduce any. I mean, there were no complications here. I mean, that will come in the next semester. I mean, next session, this session now. No impacts of immobilization, etc., and no diffusion. So really, as you all know, it was an ideal PFR. So ideal PFR is essentially a batch in time. So really, the volume that is the volume that has to be found out. If you know the flow rate, then essentially that was the time or tau here, but this is really the integration of the equation. So as far as we are concerned, we want to know how long it takes for the conversion to go from whatever S naught to some value S, and what is the time required. And so that really translates to velocity, the ds by dt really actually equal to v. And can you tell me what is v? Vf minus v. But you know, the more logical expression is what is it? Vf, I don't remember. Vf, go ahead. Vfs upon ks.
So
Into 1 minus rho into, and actually I can take the s here and write it like this: s upon 1 plus s by ks and plus p by kp. Really, that was the argument, isn't it? And because this is an irritating integration, I sort of ended up simplifying this stuff, because I didn't want you to make a problem this should not be an ability to integrate. So you remember your Haldane relationships, and what I did was that Haldane relationship is what is it? Vf s upon what is it? I don't. So the forward and the reaction reversible. So this is S equilibrium obviously upon Ks is equal to Vr P equilibrium upon Kp. And therefore, because they're equal at equilibrium. And so really what happens is that what I did was that I gave you the K equilibrium as P equilibrium upon S equilibrium as 1 by 3. And I also told you that Vr by Vf was equal to 1 by 3, 75%. This is 75% conversion. So essentially, this was to sort of make sure that Ks and Kp are equal. And so if Ks and Kp are equal, then that simplifies the integration a lot, because P is nothing but S naught minus S. And so this expression here becomes 1 plus S by Ks plus S naught minus S by Ks again, right? And then this simply becomes 1 plus S naught by Ks. So which is a constant. This is a constant, right? So that was the whole idea, to sort of make life easy, to sort of ensure that this is a constant and this is a constant. Then you can see, yeah, go ahead.
Sir, how is Ks equals to Kp? I think it should be 1 by 9.
Just think about it.
Sir, as Vr divided by Vf is also 1 by 3, and P equilibrium divided by S equilibrium is also 1 by 3. So Ks should be 9 Kp.
So bring it here. Oh, okay. Have I written it wrong, incorrectly?
Yes. No, sir. In exam, it was like I got 1 by 9th relation.
You got 1 by 9. Let me see. Or maybe it is 1 by 9. Maybe you're right. I don't know. I was trying to do it very quickly. But what is the Haldane relationship? Okay, let us rub it out and sort of do it very carefully here. If it is 1/9, then the integration will become a bit more irritating, and then the problem becomes a bit tougher. Let us do this. Usually, if the reaction, forward reaction, yes, actually you're right. I think I made a mistake. Oh wow, yeah, you're right. Actually, I should have put it the other way around. I should have put it 3 because VF. You are right. So we have I made a mess. Now this problem becomes more irritating because I think K equilibrium is equal to what? Can you tell me Haldane relationship? All of you. I mean, essentially, K equilibrium is equal to P equilibrium upon. I know I should have said 75% the other way around. I should have put it as 1/3. You are absolutely correct. I mean, I made a mistake. So P equilibrium by this, which is 1/3, because only 1/3 of the product is made. So actually, the reverse reaction is faster. I sort of made a mistake. I think this is because I should have got 75% conversion, but I wrote 25% conversion. In which case, the forward, if there is 25% conversion, and so in the equilibrium 75 and 25 are equals, and obviously this reaction rate is actually faster, and this reaction rate is actually slower. So by definition, I should have chosen a value of forward reaction max as I should have chosen it as 1/3. Okay. So sorry for that, because you obviously realize that at equilibrium only then will KSB be equal to KB. Oh. So a lot of trouble for you guys now, unfortunately, because then obviously you have to do the integration the hard way. You're right. So this will now become 1/9. So actually S plus S0 minus S upon, this is upon 5, and this will be upon 5/9, because this is KS is 5 and the KP is 5/9, right? Which is some point whatever. And so this integration becomes much more irritating. But yeah, then of course we don't get a simplification. But even this is a solvable expression. How many of you could solve it? This integration is by parts now. Hello? Silly mistake on my part, reversing has made all the problems. How many of you could solve it?
So I took a sort of a different approach. So for a PFR, I wrote like the standard equation is dF by dV equal to the rate of the reaction. And this is always.
So then, no. How can you take a different approach from this expression? There's no other approach. Only thing is, I thought that this would be simple, but it is no longer simple. It's a more tedious equation. It is still
not
going
exactly, sir. But like for a PFR, we write the general equation, right? Like in the enzyme science, not the enzyme science, in the CRE courses, we learned that we write dF by dV equal to like the rate of the reaction. And the rate equation you can write in the forms of S and KP and S and KS and P and KP, and then using that you can integrate. So like obviously it's a similar approach.
It has to be, yeah. I mean, finally, the PFR is nothing but a batch reactor in time, isn't it? This zone here is T is equal to 0, and this zone here is some T is equal to T, where this is the, if you know the velocity of the, I mean, if you know the volume. So if flow rate is F and volume is F, so this is the volume covered. Time required is T, where this is governed by this, and so the total residence time here is nothing but the. So this particle will move here if it is an ideal PFR. Of course, it will be distribution more complicated otherwise. So T0 to T whatever tau is the time for which the reaction proceeds. Does that not make sense?
Yes.
So PFR, these zones are nothing but a batch progressing through time, isn't it?
Yes, sir.
So effectively, whatever you do, finally you have to end up with this equation. ds by dt is equal to v, and v is now changing, and because of my silly error, I have now made this integration slightly more irritating. because now you will have to write VF by KS, and then 1 minus rho is 1 minus rho is S naught minus S upon K equilibrium, which is 1 by 3, and then this will be again S. So this S will go, but the denominator will not go. The denominator will be 1 plus S by 5 plus S naught minus S upon 5 by 9. Unfortunately, this is what has made all the problem. This 9, if it had gone away, if it had, as I had originally planned, then this would have become S naught and this would have become a constant. And so you would have an expression of, you would have a very simple exponential function, which would have been easy to integrate. But now this integration becomes more irritating.
Sir, I had a doubt that what will be the limits of the DS? Like, what will be the limits we take, lower limits and upper limits for
S starting point? What was the starting point of S?
Sir, S naught.
So remember that the input, what is S naught? It has to be in millimolars. What is the molecular weight of sugar? 180. So what was the concentration of sugar?
So it was 100 into 180.
100 grams, 10%, wasn't it? No.
Yes, sir.
Sorry, I forgot. Sorry, I don't remember exactly. What was the concentration? 10% or 20%? Any of you have the question? It doesn't really matter. If it was 100 grams per liter, then this is your molarity. And so, so the moles, in terms of moles, it is about, suppose it was 100 upon 180, suppose is approximately, I don't know, 0.4, 0.55 moles.
So, but why do we have to like even take into account the molarity? We can just use the gram per liter concentration, right? Since
how
glucose and
how
fructose have
case your case is in millimoles.
Right. Yeah. Right.
Okay, so actually you have to sort of write it as 550 millimoles. S naught. And if I said whatever I said, whatever percentage conversion I wanted, because you can't convert more than and that percentage conversion, that also is determined by millimoles. So everything has to be done by dividing by 180, because without dividing you just cannot get into the fact that this K equilibrium is P equilibrium in millimoles or moles upon S equilibrium, right? So everything has to be, I mean, I don't have the problem. It's gone a long time and it's just completely left my mind what the problem was. So we're spending too much time because I don't have my problem with me, and I sort of just started teaching and I just forgot that. I thought it would be a simple enough issue. So if you know this is also, I mean, suppose it was 550. I mean, let us assume that it was 100 grams per liter. I don't remember exactly what it was. So that is 550 millimoles, and the specific conversion is 550. Let us say, I mean, if it was to be approximately 600, because I don't have a calculator with me, then the equilibrium concentration will be 150 and 450 respectively, right? And suppose you start with an integration of 550 S naught T is equal to 0 and go on to, I don't know, or 600, let us say, if it was 600 millimoles, then you go on to not, you can never reach 150 because that will be infinite time. Maybe let us say 200. Whatever is the concentration at the end of the reaction. What is the percentage conversion I have asked for? Because the maximum conversion that can take place is only 25%. Now that 25% is in terms of, doesn't really matter because fructose and psychose have the same molecular weight. So 25% conversion is also same in terms of millimoles because they have the same molecular weight. But when you are accounting for Ks, then you have to incorporate the fact that it is 5 millimolar. So you have to say that it goes from 450 millimolar, sorry, 600 millimolar to, it cannot go down to 450 because then there'll be P left over. So maybe it goes to 500 millimolar or whatever is the number that you have to calculate. That was a simple algebraic multiplication or division. Okay, so that was question number 1, and question number 2 was about, that was a more conceptual problem about, and you could have different approaches, and that is why it was an open-ended question. So you know that in a CSTR dx plus ds minus, this is an equation which I wrote is equal to mu plus x plus minus dx plus minus P mu plus X plus, and you should write these equations, and dx minus by dt is equal to mu minus X minus dx, sorry, this is plus here, dx minus and plus P mu plus X plus. And I had pointed out that you get figures like this. Now really the point was that the main point here that I said was that it takes 20 days for 5% to 20 days for it to emerge. So 20 days have passed and when it has become 5%. 20 days have passed. This is time. This is 20. This is in days. And this is percentage recombinants. Now, which means that this is a highly stable system. 20 days it has remained stable. So the emergence of plasmid free cells. Now, I told you alpha is equal to 1.2. So there are two concepts involved here. Alpha is equal to 1.2, which means that once it emerges, it sort of overtakes very quickly. But this emergence is slow because it has taken 20 days. So for calculating this time period, where it goes from say 5%, with 95% effectively recombinants to 50%, this period is sharp compared to this period. And this period, for all practical purposes, we can say that if emergence is slow, P is very small. And so to calculate this approximately, we say that let us assume, for the time being, let us assume that these are negligible compared to these values. And we know that mu minus upon mu plus is 1.2. Now, this is one concept. So we have a simpler expression which is given by this expression here, and we make this assumption, but we have to prove this assumption later on. So this is what really I wanted you to do. And now, remember that in a CSTR, this is another important concept as well. You also know that if this is mu versus S, a typical growth rate versus S plot, monod kinetics, then if mu is equal to D, then mu is equal to D here. So this is the substrate concentration, because mu is equal to D. If this is D, then this is the operating concentration of the CSTR. In a CSTR, the substrate concentration may be some S naught, but what is leaving S will be given by this concentration here, where mu is equal to D. Suppose this is 0.2. I told you this is 0.2. Now, the problem is that this cell, the mu minus is growing faster. It is 1.2 times faster. Always, because this is what has been given to you. So notice that, so the mu minus is always mu, because remember that the monod kinetics, I hope you all remember your basic monod kinetics, mu is equal to mu max S upon Km plus S, Ks plus S. So if mu is higher, then it is always higher. So notice that at this mu, at this substrate concentration, black here, the actual growth rate of these cells will be 20% higher. This is 20% higher. And because this is growing fast, in the reactor, your substrate concentration will start falling because this will be growing faster. But this is only 5%. And the remaining 95%, so the system is here, 95% is these red cells, 5% is blue cells. So as the substrate concentration falls because this cell is growing faster, notice that it will sort of decline to this substrate concentration. And so notice that the growth rate here, the red one will be growing less than 0.2 and the blue one will be going faster than 0.2. But the ratio will always remain 1.2. And so on and so forth. Till at the end, when this is 100%, notice that the substrate concentration would have fallen here. Where this cell now is growing at 0.2 and this cell is slowly getting washed out because substrate concentration has fallen to this value. Notice at this point, the substrate concentration here of the red cells was such that mu was equal to 0.2 and this was 0.24. And at the end of the run, this will be 0.2 and this will be some 0.165 or something like that. So this is how the substrate concentration is actually supposed to change from here to here. As the cells grow faster here, this grows at 0.2. This starts overtaking the population. At this point, this is going faster than 0.2 and this is going slower than 0.2. So the red is getting washed out. The blue is getting dominant in the culture. And this is how the system moves in a co-culture system. And so I thought, so if you make this assumption that they are gone, So actually the problem itself is rather simple. This is the concept that I'm trying to explain to you, but this is how it is happening. And so really, as far as the problem solution is concerned, it is easy enough. We say that mu plus, so we just sort of, because we want to get rid of this, they're anyway not there. So you can see that if we solve these two expressions without this, then we can make an approximate solution by saying ln x plus is equal to mu plus minus d into x plus. Sorry, t, what am I saying? So right, so you take this on this side, this is the solution to this equation, ln x mu minus dx plus. So this is how it will change depending on what is mu plus. Notice I'm not brought in substrate, I just showed that the substrate would change very slightly from low concentration to even lower concentration, and mu will be first equal to d and then it will be slower and slower than d. So it will keep on changing. And then ln x minus will also be mu minus minus d, but here it will be always higher than d into t. Right? So the argument that we are trying to make is that this, so what we do is we subtract these equations, and we subtract this, we get ln x minus this, which is actually ln x minus upon ln x plus, is equal to mu minus minus mu plus into d. And that is where we sort of make this approximation, which I showed you, that if this is 0.2, then this is 0.24. And as it falls, at the most it will fall to 0.165 or something, in which case this will be multiplication, this will be 0.2. So notice that the difference between the two is of course dependent, but it's approximately always 0.04. That is the second approximation that you make, because 0.2 and 0.24 is 0.04. And once you have this 0.04, then of course the problem becomes rather simple. So these two approximations, I thought as engineers you should know how to make approximations, and therefore you know, so therefore this expression here is nothing but ln x plus upon x minus, sorry, x minus upon x plus is equal to 0.04 into t. If this is indeed true, then you can find out two conditions. One initial condition at time t is equal to 0, ln x minus upon x plus is nothing but ln 0.05 upon 0.95. So obviously these solutions have a plus c here and a plus c here, so you can find out the, and so there's a constant here to find out that at t is equal to 0, this is this, and then we find out what is t when ln x minus is 0.5 upon 0.5, so which is actually just 0. So what is the time when it becomes, when this term becomes 0? So using the constant value, you can sort of find out what is the time required if this is the governing equation for x minus by x plus to go from 0.05 and 0.95 to 50-50. And that time turns out to be about 60-70 hours, which is approximately 2 days or whatever, 2 or 3 days. And so you can, your basic assumption that emergence is slow because it takes 20 days is correct, and therefore the assumption that the p is small is also validated. So there were a lot of assumptions in this, and I really wanted some of you at least to be able to state these assumptions and have a feel of the numbers that are involved rather than doing the maths in a very crude way. So I want you to have a sense of what are the numbers involved in plasmid free cell emergence or enzyme kinetics, and where and when can engineers safely ignore certain parameters or not. That really comes out from the maths, whether you can ignore certain terms or not ignore certain terms. And that is a very critical ability that most engineers should have. I mean, it is not enough to be able to solve equations and to quantify. It's also enough to be able to understand what is the level of error when we do certain approximations. So that was essentially the purpose of this question. I do not know how many of you did it because I've not checked everything. But the first question, I should really apologize. Made it unnecessarily complex, which was not my intention. I think I made a silly mistake. I should have put it as 3 rather than 1 by 3. And that would have, of course,
Sir, in the first question, V is equal to V upon F is equal to tau. So, sir, the flow rate should be equal to ds by dt, na?
Not the flow rate. The velocity is equal to ds. Hold on. Ds by dt.
Yes,
is
the velocity would be ds by dt, but the flow rate would also be equal to ds by dt because means
the flow rate is given to you.
Okay, got it. The increase flow.
So if you find out the time required for, you know, this V, so if you find out the integral of, you know, whatever is the ds function, this is ds by dt is equal to whatever function. If you find out the s from s0 to s is equal to some integral t is equal to 0
Yes,
to
sir,
t, and then this t can be found out, and then this t is equal to v upon f. So you can find out volume.
Yes, sir, got it. I was mistaken. Yes, sir, I know. Sir, one more thing. Sir, you took 450 as means the upper limit of s should be s equilibrium. The substrate concentration.
No. That if I took s as s equilibrium, this t will become equal tend to infinity as s tends to s equilibrium. This t will tend to infinity. So this you will not be able to solve it. So really s is equal to whatever is the given problem in the question. What was the question? I mean, can any of you remember it, or can I see it in my previous notes? Okay.
So it is in the files.
Yeah, let me see if we can locate the question paper. Mid-sem exam. You people have no memory at all, right? Right. So I had 100 grams per liter. Now let me sort of do. And you wish to get a Psychos concentration of 20. So you remember that. So now 120 and 5 millimolar, 15 millimolar. VF1 VR. So that is the mistake that I did. Okay, sorry. So that was the mistake I did. So so now right. So 100 grams is S0, so 100 by 180. How much is that? Into, come on, let us have some nines, right? 5 by 9. How much is that? 55.55. 0.55, so that becomes 550. Now start will go off. आप लोग मुझे स्लो डाउन मत करिए, ये आई थिंक दिस इज इजी एनफ. S0 is 550 millimolar if you are choosing K as KS as 5. So S0, and then I said 20 grams of Psychos, which means 80 grams. So 80 upon 180 is how much? 4 by 9. 9 4s are, so 440, right? So this is 550 and this is 440. So the limits of the integration are 550 to 440. Now suddenly to start trouble. The limits are 440, right? And the limits here are 0 to time t. So you have to find out t. That is all. You didn't check this. You didn't see that the final Psychos concentration is 20 grams per liter. So if S is going to P, and remember they are same molecular weight. So here you can do the subtraction and that very easily. So if this is 100 grams and this is 0, then when it becomes 20 grams, this has to become 80 grams. So the integration has to be 100 by 180 to 80 by 180. So from 550 to 440. From the silence, I assume that you have done it, or should I assume that none of you have done it? Well, you know, this stuff cannot be taught. I mean, how to put integration limits, because this is something which we have studied in class 12. So I don't want to get into that. So now let us quickly sort of move ahead, because we do need to cover stuff. So the problem of enzyme. inhibition. So inhibition kinetics, because we have done it in inhibition kinetics, we have done it in our practicals. So you're already aware of this to a certain extent, but let us sort of do it properly. And the way we understand inhibition kinetics is that we have E plus S, of course, and अरे भाई ये क्या होने लगा अचानक, this starts giving trouble. So this is working perfectly fine. It just goes crazy after some time. Yes, and then we have E plus B, right? You're all familiar with this basic model and so you're also familiar with the fact that I talked about E plus I, and this was the competitive inhibition model going to EI, and this was a dead end stuff. This was dead end. But theoretically, it is possible in a most general model that this EI can combine with S and give something like an EIS. And EIS may well then go to EI plus P, maybe slower, because you can have inhibitors which slow down the reaction, but you can have also activators. Maybe EI is an activator which speeds up the reaction. So it is not just inhibitors that we are talking about. In a most general model, we can have inhibitors as well as activators. And I is an activator, it brings the enzyme to an enhanced state, binding is with S is far better, makes EIS complex, which generates EI plus P, and then sort of this cycles again. And in the most general case, ES can theoretically, so once the enzyme has bound to the substrate, it can also bind with I, which means that there is no competition here. So these are therefore called, this part is therefore called non-competitive or uncompetitive inhibition. So if E binds with I, it becomes EI. If E binds with S, it becomes ES. That is the competitive inhibition. I and S are competing to bind with E. But even after the enzyme substrate complex has formed, I can still bind to it. Then that is a different story altogether, right? And this can then, ES plus I can also give rise to EIS. Are you getting this argument? So therefore, this is the most generalized model of kinetics. I mean, inhibition kinetics. The generalized model of inhibition kinetics where each of the possibilities are taken care of. In competitive inhibition, this part will be important. And in uncompetitive inhibition, this part will be important, and so on and so forth. And we will talk of which part is important, but this is the most general model. So all possibilities are taken care of. E binds with S forms ES, E binds with I forms EI, EI binds with S forms EIS, ES binds with I forms EIS, and by putting some of these reactions equal to 0, we can generate all the sub-models in this class. So this is a generalized model, and ES then gives E plus P. EIS may be dead end, or it may give EI plus P. And we can sort of call this as K2, as was as usual. We can call this as K3. And of course, in most usual conditions, K3 might be equal to 0, in which case this is a dead end reaction. You get my point? By choosing appropriate values of K, but solving this generalized model, we can actually take care of all possible inhibition kinetic models. So this is the most generalized model. So before I begin, let me ask you a very simple question. Can we sort of determine, I should rub this out, but anyway, I'll not rub this out. I hope you can see. So can you see this basic structure, base structure here, this 4? Just focus on these 4. And please remember that for any circular reaction like this, there are certain basic rules, right? So for example, here is Ki, and let us forget this part for the time being, and let us simply look at these 4. So we know that they are not, all 4 are not independent. So for example, I can write this here. Oh, sorry. Let me sort of write this here as Ki, right? We wrote this as Ki and we wrote this as Ks, right? So what is Ki? Can some of you tell me, one of you? What is Ki?
EI upon E into I.
E into I upon EI.
Yes, sir. E into I upon E.
Right, E into I upon Ki, because this is the dissociation constant. We always write it in terms of, and this Km, which we usually call Ks, but let us keep it as Ks, right? Or Km, whichever way you want it. Km, I don't know what you prefer. Km is equal to E into S upon Es. Is that all right? Hello? Yeah. And so, is it okay? All of you fine with this? And let me say
Yes, sir.
that this I write, and I will explain why. Let me write this as Ki upon A. Opposite this, the mirror image of this. And let me write this as Km upon A, upon B. How can it be A and B? Okay. So now what is Ki upon A? It is some, I mean, this ES. So really what I'm saying is that enzyme binds with inhibitor with the dissociation constant of EI, Ki, and ES binds with inhibitor with a dissociation constant of Ki by A. And please think about whether A will be 0 or infinity, depending on whether this reaction is moving forward at all or not. What is Ki by A?
ES into I upon EIS.
Yeah, so Ki by A is equal to ES. Oh no, this is a problem. Is it working? Yeah. ES into I upon EIS. And similarly, Km by B is equal to EI into S upon EIS. Do now realize something very obvious. We can sort of, EI can be written as, and ES can be, ES here can be written as a certain way, EI can be written as a certain way. So can you now tell me? So
Sir,
let us take this expression first and let us do a little bit of algebra here.
ES can be
Yeah.
written as E into S upon Km, and EI can be written as E into I upon Ki.
Yeah, and so do you realize that the expression for E into S into I upon EIS, ESI, sorry, ESI, whichever you want to write it, can be written as what? From two ways. It can be reached from two ways, and can you tell me what are the two ways and what are the values therefore? So one is A into Ki into Km, right? Oh, the hell. So one is A into Ki into, come on, K into Km. Is it all right? This is one expression. No, I think I should, I'll wait for a minute and want you to do it on paper and pen, because you know listening is not a good idea. And what is the other expression? Just let me wait here and listen. Yeah. So is this all right? So approach EIS from this direction and approach EIS from this direction, and they should all be the same. So therefore, for circular reactions, really what I want to ask you, and this is something which I want you to think, that certain variables, they're not four independent variables. That is all that I'm trying to tell you. So what do I get here? If we go like this and we go like this, so obviously you can see that this will not be, this will be Ki, Km, B. And so the same way you will get, come on, I think some of you should say this. Look at this expression, man. What is it? Is it so difficult? Okay, I will ask you the simple question. What is A in terms of B? Hello? Can you hear me? Or is it gone? Hello?
So we can.
Is it okay? Can you hear me? Hello?
Oh, yes, sir, we can hear.
You can hear me?
Yes,
You can
sir.
see the, yeah. So, yeah. So, so can you just sort of, where is it? Can you tell me the relationship between A and B by approaching EIS from this? So EI, first EI upon by this expression here, and then using the next expression there. So tell me what is the relationship between A and B?
Sir, A would be equal to B and both would be equal to 1, I guess.
Yeah,
No,
not
sir.
equal to 1. They will not be equal to 1.
Yes.
So I can write this as Km by A and this as Ki by A. That is all I'm trying to say. We don't need to choose A and B two parameters. By definition, A will be equal to B because if I approach this by this side and I determine this expression here, ESI by ESI, you will get A Ki Km, and if I approach it from this side, I will get B Ki Km. Okay, and therefore I will know that B and A are the same terms. So I need, so if this is the same argument which I was trying to do in a reverse fashion and failed so miserably, that I was trying to make Kp equal to Ks by putting Bf equal to Vs and 50%, then it would have been equal. So Ki, this is Ki by A. So if this is Km, this will be Km by A.
So shouldn't it be Ki into Km by A, like ESI by ESI? Like why is the A in the
Let us do it. I mean, as a matter of fact, this is precisely the kind of thing I want you people to catch. Let us do it. So what is it? Let us do it slowly. So what do you get? EI is equal to, so this is Ki by A, right? So tell me what, okay, shall I do it for you or will you people do it? All of you get. So what is EI? What is EI? Sorry.
E into I by Ki.
E into I by Ki into S, right, upon EIS is equal to what?
Km by B.
Km by B. Right? So what do we get?
So Ki goes there. So Ki Km by B or Ki Km by A.
So Ki Km by B, right, is equal to E into I into S upon EIS.
Yes.
Right? And what about this way around?
So it will be Km into Ki by A.
So that's it. So that is the same thing, right? Ki Km by A, Ki Km by A will be equal to the same thing. So therefore A and B are the same. So that's what I'm trying to prove to you. Right? Is it all right now? So Ki Km
Yes, sir.
by A is equal to E into this term here or this term here are both equal to E into I into S upon EIS. Is this all right? Okay. So now let us now do the thing very obviously. It's very obvious now and how we proceed. Remember how we did this? So I should not have rubbed the whole thing out. But anyway, doesn't matter. V is equal to, the velocity of reaction is equal to, there are two things, right? So let us assume for the time being, okay, I should have, you remember the plot, right? So let us assume that it is K2 ES. Or let us say plus K3, why not? K3 ESI. Right? And so really now we have the other expression ET, which is what we are going to do, is equal to E. Remember the fractional saturation? Sorry, not E, just E. What was it? E plus
ES plus ESI plus EI.
Yes, absolutely. It's EI plus ESI. And now all these things can be written in terms of a very simple expression. So really the fractional saturation is, if let us forget this first, for the time being, let us forget this. So if fractional saturation, as far as ES, fractional saturation, if this is only the reaction here, K2 into ES, the fractional saturation is nothing but ES upon E plus ES plus EI plus ESI, right? And of course, all of these can be written in terms of E and then divided by E. So what is ES? Sorry, EIS. EIS. So what is ES?
Sir, E into S upon Km.
So E into S upon Km, and this is E plus E into S upon Km plus E into I upon Ki plus E into I into S upon A Km Ki. सॉरी Km by Ki by A किया था ना, उल्टा A मैंने इधर रखा था, ऊपर रखा था कि नीचे रखा था? नीचे रखा था ना, सो वो ऊपर चला जाएगा अपॉन Km Ki by A. Is this all right? And then we divide by E and we can get the fractional saturation as S by Km upon 1 plus S by Km plus I by Ki plus I into S by Ki Km into A. Some A will come on top, right? Is this all right? Or did I go too fast? This is obvious, right?
Yes, sir.
So we have now a simple expression, and of course, if this was important, and we were looking at fractional saturation with respect to ESI, that's also easy enough. And of course, and once you know the fractional saturation in terms of S, then you know the reaction rate of reaction is K2 into this. So we write into K2. So V becomes equal to K2 into fractional saturation, which is your K cat. So K2 here. And you can see, for example, at least you can see very clearly that competitive inhibition, this part is disappeared. So the competitive inhibition model becomes K2 into S, and I multiply by Km, then I can get Km plus S plus I into Km Ki. Can you see this?
So could you explain why did you
okay.
the rate equation?
Sorry.
So from the rate equation, why did you cancel out the K3 ESI?
I did not cancel K3 ESI. Oh no, that was not cancelled out. I would say let us assume that ESI is a dead-end complex. Assume that this is a dead-end complex. For the time being, assume dead-end complex. Now dead-end complex simply means that K3 is equal to 0. If K3 is non-zero, so if it is non-zero, then let us write. मैं इसको मिटाना नहीं चाहता हूँ, असल में और कुछ नहीं था, बस बोर्ड से बचना चाहता था. चलिए मैं कोशिश करता हूँ. So in which case, if this is non-zero, then we need to find out the fractional saturation with respect to ESI. In which case the fractional saturation with respect to ESI is nothing but ESI divided by this E plus this. So now what is ESI equal to? Okay, let me write it.
E into I into S by
plus EI plus ESI. And then this can be written as, I'm trying to wipe this out, that is why I don't want to wipe this last equation out. So this, instead of this fractional saturation, I now have a fractional saturation given by another expression here, which is E into S into I divided by Ki Km into A here, right? Divided by E plus, as I said, E into, sorry, क्या कर रहा हूं मैं, E into S upon Km plus E into I by Ki plus E into I into S upon, so you see the advantage, Ki Km into A, and then I divide by E, I get this as 1 and these are all gone. And so this is the expression for the fraction saturation in terms of S. Notice again, S and I. And then this multiplied by K3 becomes the velocity if that is, if this assumption is not correct. So K2 into this plus K3 into this. And notice that by putting appropriate terms equal to 0, either K3 equal to 0 or whatever terms, we can now manage to generate almost all the possible combinations of inhibitions that we need to do. So I will stop here and I want you to think about this. So this is the simple algebra. Now this, you see how advantageous this is. This algebra makes for very simple calculations of fractional saturation from the basically the dissociation equilibrium equation. From dissociation equilibrium, you can write everything in terms of E and S and I separately, and from there you can simply divide by E and write E, the effective E, the E which is participating in the reaction as ES. So reaction is K2 ES and divided it by ET. Remembering that K2 ET, when every is nothing but Vmax. Every molecule is involved in the forward reaction, that is the maximum reaction. But you have K2 into fractional saturation. So this here, Vmax into whatever is the fractional saturation. In the simplest Monod kinetics, it was S upon Km plus S. In the case of inhibition kinetics, Km 1 Km plus S plus I by Ki. Can you see? Can you see the simplicity of the formulation?
Yes, sir.
So Vmax is K2 into ET. Fractional saturation is whichever thing is participating in the reaction divided by ET. And so Vmax is K2 ET into the fractional saturation, S upon Km plus S, or S upon Km plus S plus I by Ki, or S upon Km plus S plus Km plus S plus I by Ki plus, sorry, here, plus AI into S upon Km Ki. This, of course, if only ES is. Otherwise, this plus this as well. So, you can simply look at the fractional saturation, the sites which are the amount of total enzyme. So really, we are all the time looking at the ES by ET, or if ESI is active, ESI by ET. I want you to go back and do this algebra. It's simple enough so that you can practice. And then from there, we can derive all kinds of forms of inhibition kinetics, depending on which of the parameters is important and which of them is not important. So stop here.
Sir, this is the velocity of reaction in case of competitive inhibition. K2 S
No.
by Km.
भाई आप लोग तो बड़ा मुश्किल कर देंगे. अगर competitive inhibition है तो आपका केस ये होगा. Can you see me? ये होगा competitive inhibition. सिर्फ इतना.
Yes, sir.
ये तो मैंने जनरल मॉडल बनाया है. This is a general model. As a matter of fact, this is not the complete general model. This plus this is the general model. This plus this is the general model. But
yes,
if we assume dead-end complex, then we can ignore this. If we assume dead-end complex, we can ignore this. Then this is the general model. Right?
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Okay. So that is what I'm trying to say. So it is a simple algebra by looking at the fractional saturation of the enzyme vis-a-vis substrate or whatever it is the complex which generates the product, and finding out the fractional saturation. So that is the total saturation, and then expressing the reaction velocity as a maximum velocity into the fractional saturation. Okay.
Yes, sir.
So the concept is clear to you, all of you?
Yes, sir.
Okay.
So I had a small
Thank you.
question. It isn't related to like inhibition. I just wanted to know, sir, what happens if we have multiple substrates, like instead of a single substrate?
We will come to that. If we get the time, we will talk of multiple substrate reactions. And I have loaded a book in the class notes. I hope you have seen it. Two books,
sir.
I think.
Yes, sir.
So read the easier one, the Sorrow book. It has, the problem with that book is that it has lots and lots of errors. छोटे-छोटे mistakes हैं, मतलब typos and calculations, और कभी A ऊपर लिख दिया, कभी E नीचे लिख दिया है. But essentially, exactly like me, I think it's almost like a classroom notes with lots of mistakes the way I make. But you know, read through it. In the later part, it does cover a little bit of the algebraic equations and the approximations and multi-substrate systems. I will come to them in a while. I want to not focus too much on kinetics. I want to get back into enzyme engineering with practical issues like immobilization, mass transfer kinetics, diffusion plus enzyme reaction. These are the things. Have you studied diffusion plus kinetics?
No, sir.
Hello.
No,
आप
sir.
लोगों ने थील मॉडुलस वगैरह नहीं पढ़ा है?
No, sir.
No. Oh my God. So I'll have to derive the Thiel modulus. All right, fine. We'll sit and derive it. I will assume that you are telling the truth. I thought reaction engineering में कहीं ना कहीं mass transfer coupled with enzyme with normal kinetics is always taught, but coupling it with enzyme kinetics is a more tricky business. We'll come to that because the practicals, that is why I have stopped. The practicals will be on immobilized enzymes. Of course, you will not actually immobilize it. So you need to understand how immobilization impacts on enzyme efficiency. You understand, right? So the enzyme is sitting inside a matrix. So obviously the substrate concentration that the enzyme sees is the rate of reaction. So it is a function of the S. Enzyme kinetics is a function of S, but this S value is determined now by diffusion. So this S value inside a pellet is not the same as the S value outside. So you have to couple the diffusion to find out S, and from that S find out the rate of reaction. So not a very difficult job, conceptually easy enough, little bit of math. Is it clear to all of you? This part at least? We'll come to those in a time, sometime. Any questions? So we stop here?
Sure, sir. Thank you, sir.
Yeah. I don't know where I was.
Thank you, sir.
Okay, thank you. Achha.